Welcome to this explainer. Today we're going to skip right past those vague headlines and map out the actual physical audit trail of a single AI prompt. We're talking the entire journey, from the smartphone in your hand all the way down to the regional power grid. You know, we constantly hear these sweeping claims about AI's environmental cost, and it's usually wrapped up in this invisible, floaty metaphor of the cloud. But spoiler alert, there is no cloud. There are just physical machines pulling real power from very real grids. So let's take a look at the system beneath.
Okay, so let's anchor ourselves in physical causality here. Think about a completely everyday action. Say you ask an AI assistant to plan out a dinner menu for the week. It feels like magic, right? But the absolute millisecond you hit send, you are triggering a massive physical chain reaction. You're engaging real silicon, generating real heat, and demanding real electricity. To understand AI's true footprint, we actually have to trace that exact request.
Here is our roadmap for the audit today. We're going to zoom out step by step, starting with the physical AI request itself, looking at the facility measurement boundary, diving into a specific 0.24 watt-hour benchmark, exploring how this hits the local grid, and finally, figuring out how to evaluate all these AI energy claims we see in the news.
All right, let's dive right into part 1, tracing that physical request all the way down to the silicon.
Following the data path, your single request moves from the external network and app routing straight down into the server rack. And it doesn't just hit one magic brain. It triggers a whole sequence of events. It hits supporting models for classification, it activates the heavy-lifting AI accelerators for the actual processing, and it relies heavily on the host CPU and DRAM. But here's a totally critical failure point that so many people miss. To ensure your prompt is answered in milliseconds, the system requires critically reserved idle machine capacity. That means servers are literally sitting there drawing power right now, just waiting to handle sudden traffic spikes.
Which brings us nicely to step 2. We have to zoom out to the facility measurement boundary because we can't just look at the computer chip in isolation.
What's really fascinating here is how clearly organizations like the EPA and Green Grid establish these exact measurement boundaries. When you map out a dedicated data center or a mixed-use building, you have to audit every single energy stream. We're talking about chilled water, natural gas, power conversion losses, the whole shebang. Because if you're only measuring the electricity going directly into that AI chip, you are missing a massive chunk of the physical reality. The building itself is practically a giant machine that requires immense power just to keep those servers from melting down.
To actually account for all that facility overhead, like the power conversion and those liquid cooling loops, the industry uses a really important metric called PUE, or Power Usage Effectiveness. It's pretty straightforward. It simply divides the total building energy by the energy used specifically by the IT equipment. It's essentially a multiplier, and it's absolutely crucial. You simply cannot know the true energy cost of an AI prompt without factoring in the PUE of the facility it was processed in.
Okay, let's move on to step 3 and see how this builds into an actual measurement by looking at a highly specific, bounded case study. Back in May 2025, Google comprehensively measured their median Gemini Apps text prompt, and it clocked in at exactly 0.24 watt-hours. This brilliantly illustrates that full production stack we've been talking about. If we break it down, yes, the active AI accelerator chip uses the most power at 58%, but look at the rest of the system. The CPU and DRAM take 25%. Those idle systems we mentioned waiting for the prompt take 10%, and the facility cooling and overhead make up another 8%. So together, the supporting systems are making up nearly half the energy demand of the prompt itself.
Now, to put the physics of this specific 0.24 watt-hour benchmark into some everyday perspective, that is less energy than watching just 9 seconds of a modern 100-watt television. And when it comes to the physical cooling happening in that facility, the water consumed for that single prompt is 0.26 milliliters. To visualize that, it is precisely the equivalent of just 5 drops of water. This is orders of magnitude lower than some of the wilder estimates out there, specifically because this is a properly measured production environment, not some unoptimized benchmark.
So as you can see, definitions matter entirely. If you were to use an older, narrow measurement boundary that completely ignores those idle machines and the facility's power usage effectiveness, you'd incorrectly estimate the prompt's cost at just 0.10 watt-hours. By ignoring the physical reality of the data center, a narrow boundary undercounts the true physical energy by more than half. This is exactly why you always have to ask what is actually being measured.
But hey, here's the bright spot in tracking the full, comprehensive stack. It properly exposes the hotspots and actually incentivizes optimization.
By applying this rigorous measurement, Google was able to track massive efficiency gains. Check this out. Over a single 12-month period, software efficiencies and clean energy procurement drove a 33 times reduction in energy consumption per prompt and a staggering 44 times reduction in total carbon emissions. So, efficiency per task is rapidly improving, provided you're actually measuring the full system.
All right, shifting gears to section 4. Let's zoom all the way out from the facility meter to the macro scale, where all these billions of tiny prompts hit the regional grid.
Before we measure the macro grid's stress, we absolutely must clear up two terms that constantly get conflated in headlines: energy and power. They are not the same thing. Energy, which is measured in annual terawatt hours, is the total electricity consumed over a long period, like a year. Power, on the other hand, is measured in peak megawatts, and it's the instantaneous rate of electricity flow. Power is what actually causes the physical wires to heat up. Power is what causes local grid bottlenecks.
If we look at total energy over time, the International Energy Agency estimates that all U.S. data centers combined, and that's all of them, not just AI, accounted for about 4% of total U.S. electricity demand in 2022, potentially rising to 6% by 2026. And looking further out, Berkeley Labs scenario estimates for 2030 show similar macro-level growth. Now, while that's significant, a single-digit national percentage doesn't exactly sound like an immediate apocalyptic crisis, right?
But here is the massive contrast. The consequential bottleneck isn't that global or national energy average, it is local peak power. The North American Electric Reliability Corporation, or NERC, projects a huge build-out of data centers. In specific Western load areas, known as the weak assessment areas, they project that planned data centers could consume up to 40% of local peak demand. 40%! That is where the actual physical friction happens. The challenge of AI isn't necessarily draining the world's total energy supply, it's about potentially overwhelming specific, local power substations at peak times.
So, with efficiency improving but overall demand surging, how do we make sense of this? Let's finish up with Section 5, building your interrogators toolkit for evaluating these claims. You can and should interrogate any AI energy claim by demanding the physical details using 3 simple questions. Number 1, what exact AI task is being performed? Are they citing a highly optimized text prompt, a heavy video generation, or a massive, months-long training run? Number 2, what measurement boundary was used? Did they just measure the chip, or did they include those idle servers and the facility cooling? And number 3, what scale and location are they actually talking about? Are they confusing a local substation's peak power bottleneck with the entire global energy supply?
Ultimately, the cloud is just a comforting metaphor for physical machines pulling real power from real grids. Every single prompt you send leaves a physical audit trail from your device, through the network, down to the humming server racks, and out to the power lines. So the next time someone throws out a dramatic, context-free statistic about artificial intelligence, will you ask for the physical audit trail? Will you demand to see the system beneath? Thanks for joining me on this explainer. Keep questioning and always look beneath the surface.